PLC counter instructions. They are very, very similar in operation to timers. You think about it as timers are counting time slices and counters are counting events. Okay. Hopefully by the time we get done with today and labs, you guys will be able to do counters in your sleep. You're going to hopefully be able to use count up instructions, count down instructions to create ladder diagrams, reset them. That, by the way, is the same reset command as the one used for timers. Connect different counters in Cascade like we did the timers. Use timer and counter together to create ladder diagrams. Much like the timers, this slide is completely bogus. There is no such thing as a double input counter in the Rockwell automation world. Does not exist. Like I said earlier, the counter instruction is similar to the timer instruction, displayed in block format, single input. Umbrella MicroLogic series programmable controller uses one input, so does every other Rockwell controller. You can address them from C5:0 all the way up to C5:255, so there's a total of 256 of them. Count up, accumulated register value increments. Whenever the counter device, the counter input device changes state. That's not quite enough information. It has to see a transition from 0 to a 1. The conditional logic. Okay. So from false to true, it does not count when it goes from true to false. Okay. Count down, accumulated value decrements, or counts down whenever the counter input device changes state. Again, false to true transition for other conditional logic. Okay. There are some caveats about the count down we're going to talk about here in a little bit, but for the most part, they operate pretty much the same. Okay. In this case, every time switch 1 goes from false to true, we get a count up from 0 to 10. Unlike a timer, the counter will count past its preset value. Okay, so if you close switch 1 11 times, it'll count the 11th one, 12, 13, and so on, up to its limit of 32,767. Okay. Preset basically determines when the done bit is going to set. Okay. There are ways to program around that so that when the counter gets done, it's just done. It won't increment anymore, or decrement, depending upon what it is. Likewise, if you close switch 2, it's going to count down. I don't know if you guys noticed this or not, but the old pause for effect thing. Count up, the preset's 10. Count down, preset is negative 15. That's what is the difference between the two. They both start at 0. If you start at 0 and you decrement, by definition, you have to go into negative values, right? The counter instruction, like the timer, contains a couple of registers. Preset register holds preset number, accumulated holds the accumulated number. Status registers help the PLC keep track of the operation of the counter. 2 flag bits, count and done. There are a couple more, but we're really not going to concern ourselves with those just yet. There they are. Overflow, underflow, and update accumulator. The overflow is if you try to count more than 32,767, it wraps around to negative 32,768. And an underflow is if you try to count below negative 32,768, it wraps around to 32,767. Okay, that's when those 2 bits set. Tells you that you went past the capabilities of the counter itself. Okay. Count up, accumulated register increments when the counter input device changes state from negative to positive, or from false to true. Reset instruction is used to reset the accumulated register back to 0. Okay. Notice that is an actual reset. It is not an OTE that is labeled RES. It is a reset command. And you have to put in the address of the counter itself for the reset. Ladder diagram using count up. Press the push button and the counter will increment once per press. While it is not done, XIO there. When it's not done, the green pilot light is on. When it gets done, green turns off, red turns on, and then of course switch 1 does the reset. Count down, the accumulated the accumulated register decrements when a counter input device changes state from false to true. Reset value for countdown is usually a negative number. If you want the counter to work like it's supposed to, it must be a negative number. Content of the accumulated register decrements from its initial value of 0 to a negative preset. And then, of course, the reset resets it back to 0. Okay. Count and structure comparison. Count down, done bit, resets to 0, done coil de-energizes when the content of the accumulated register decrements past the preset number. Keyword there is past. So when your lab sheet tells you that you have to press the button 14 times for the countdown instruction, you have to put in a negative 13 in your preset value. So the 14th press will shut the done bit off. Okay. Count up. Done bit is enabled when the accumulated register is equal to or greater than content preset. Okay. So that actually holds true for both of them. So the accumulated value is equal to or greater than preset the done bit is going to be set. connecting the instructions. Contents to an entire section of a conveyor needs to be known at one time. So you place two proximity sensors on the conveyor. One is connected to count up, the other one is connected to count down. As things move on to the conveyor, you have to count up, counts up, and then as they leave, count down, counts down. In order for that to work, you have to have count up and count down both addressed to the same counter. Okay? So C50, for instance, count up on this end is going to increment every time a new widget comes onto the conveyor, and then you have to count down on this end, addressed to the exact same thing. Okay. In-feed procs connected to count up, out-feed connected to count down. Cascading counters, some industrial applications, counters are cascaded so that one counter increments or decrements when another counter is done, used mainly in material handling, process control environments. So you can think about packaging operation where you put 12 cans in a box, and then you can put 12 boxes on a pallet. So every time counter one counts 12 cans, that's one box. 12 more cans, another box. 12 more cans, another box. Okay, does that make sense? Ladder diagram using cascading counters. Push button in this case increments the count up C50. And then when the done bit gets set, that increments the second count up C51. When C51 is done, turns on the green pilot light. And switch for the done bit on C50 will reset C50, so every time it counts up to 10, done bit sets, increments this counter, and then it resets itself. Only way to reset the whole thing is with the switch. Ladder with counters and timers. In this case, it is counting. That's really hard to see. You know? Okay. On delay timer, 1 second. Every time the timer gets done, C50 increments. Every time you get to 60 seconds, done bit sets, increments the minute counter. And resets the seconds counter. Every time you get 60 seconds, or sorry, 60 minutes, increments the hours counter, resets the minutes, and so on. Okay, but relatively easy to follow, I mean. Okay. Okay. In this activity, we're going to create a PLC ladder logic diagram that carries out the following operations. Fan is to be turned on when counter 0 counts down from 7 to 0, and when either counter 1 counts up to 14 or counter 2 counts down from 14 to 0. And then one switch will reset the entire process. Okay. That's all right. Okay. Doesn't really say. Do normally on push buttons, okay. So, inputs. Do normally on push buttons. Okay, want to use red and red, red and green, red and green. Red and green, okay.
Christmas.
It's also a good TV show.
That's awesome.
So, 6 and 8. And then one selector switch, which is the only selector switch we have. And output, we just have the fan. Use 08. What one? Oh, for the second one, so I need all power by okay. So, which button we wanted to use for counter 0?
2.
We're going to need 3 push buttons, aren't we? We're going to increment 3 counters, or operate 3 counters. So, you want to use the other ribbon or the other thing? What about counter 1, what we want to use for that one? Red or green?
Red.
Well, either green or red. So, wait, button 3, close enough. Okay, and then the switch resets. Okay. So say 5, 0, and 1 or 2. I'm going to turn fan on when they're done, right? Okay, so counter 0. We want to be count up, count down.
Down.
Okay. What's the preset going to
-7.
be?
-8.
Mm-hmm.
-10.
Mm-hmm.
So,
6.
14.
You're getting farther away.
Oh.
It's -6. Supposed to press the button 7 times. And I wrote -7 anyway, didn't I? -6. Start at 0. Press the first time, that is -1, -2, -3, -4, -5, -6 is, then you go -7. -7 is less than -6, right? So by our definition, the accumulated value is equal to or greater than the preset. 0 is greater than -6, -1 is greater than -6, and so on. -6 is equal to -6, -7 is less than -6. So if you want to push the button 7 times, counting down, you have to set your preset at -6. Okay? about counter number one? Count up, count down.
Up.
Okay. What's preset? What is it?
Is it?
Louder. What'd you say?
You said 13.
Incorrect.
14?
14. We're counting up. Equal to or greater than, set the done bit. Means you gotta get to at least 14 for it to be equal to or greater than the preset value. Right? Okay, what about counter two? Up or down? Preset value.
Negative 13.
Okay. When do we want the fan to work?
Negative 14.
Is that what the narrative said?
When counter 0 counts down from 7 to 0, and when either counter 1 counts up to 14 or counter 2 counts down from 14.
Okay. So when is this going to evaluate as true? Do we want it to be XIO or XIC? Counter 0. Think about when the bit is going to be set, when it's going to be clear.
Fail.
XIO. Because 0 is greater than -6. Accumulated value greater than or equal to preset done bit. Okay, so before we do anything else, that done bit's going to be set. Okay, so in order for that to evaluate as false, when we're first starting out, it has to be an XIO instruction. Okay? What about C51?
XIC?
XIC, correct. Because when we start out, 0 is less than 14, so the done bit's going to be clear. Okay, what about C52?
XIO.
XIO for the same reason C50 is XIO. Now, with me. In order to prevent the counters from going past the preset values, you can look at the done bit. Okay. So when the counter is not done, we want it to count. So counter 0, do we want this to be XIO or XIC?
XIO.
You sure? When's the done bit going to be set?
Times 0.
Can't have your fingers in your mouth.
Sorry, is it at 0?
When is the done bid set? Accumulated value is equal to or greater than. We already established that 0 is greater than -6. Which means the done bid is going to be set whenever you start. So in order to get true, operate the counter, if the done bid is going to be set whenever you start, how do we look for a 1? XIC. Okay, what about count of 1? It's going to be XIO because the done bid is going to be clear when we start. And what about 2 Enter
XIC.
Okay. There is one more law in that program. Anybody spot it? I'll take that as a no. When you turn that switch on, reset all of them. That's going to be true. That's going to be true. So if I have a true, false, true, am I writing a 1 or a 0 here? Writing a 1. So when you are resetting the counters, hands on. Erica doesn't say anything at all about resetting counters, turn the fan on, so we gotta fix it. Okay? So anybody have a thought on the easiest way to do that?
That'd be the selector. Switch. Oh, no, it's reset.
Like that? Input 01, right? I suppose I should put the address up there. Okay, so do I want that to be XI or XIC?
Obviously.
XIC?
Excellent.
That means I have to have the reset switch on in order for my fan to do anything at all,
The opposite of that.
which is
Yeah.
it's XIO. My reset it on, I want this to evaluate as false, preventing my fan from running. Okay? So you see how that works, how we figure out what needs to be where and whatnot? Okay.